Hi all, welcome back to systemverilog sessions. In this video, I'm going to discuss about systemverilog interface. So what is interface? What is the need of interface? What are all the features we can include in the interface? What is mod ports? What is clocking blocks? Virtual interface? Everything we will see. Okay. But in this video, I'm not going to cover everything. We will see interface, virtual interface and few examples. Okay. So what is the need of interface? First of all, we'll understand what is interface. Interface is a block or construct which encapsulates the signals to communicate between multiple blocks. Okay, so interface is a bundle of signals or nets which is used to communicate between multiple modules. Module in the sense your test bench or DUT, or multiple modules if you have other modules also, slave, master. So you can use the interface. So if you see here, this side I have a test bench and this side I have a DUT. So test bench and DUT is connected with multiple nets and signals. So this is in Verilog. If you want to connect between test bench and DUT, you have to manually declare all the signals, all the nets and signals. But when we use the interface, systemverilog interface, it encapsulates all these nets and signals, and we can use the interface as a single port. If you see here, multiple ports I have between test bench and DUT. If we use the interface only, we can use single port. So this is the interface. Inside the interface we have all these signals, and when you want to access the particular signal, you have to use dot. So interface dot, that signal name. Okay, so test bench and DUT can be connected with interface. Interface is a block or construct which encapsulates the signals to communicate between test bench and DUT. So it simplifies complex connections. Complex connections in the sense, as I said before, instead of declaring all the signals individually, we can use the interface as a single port, right? So it simplifies the complex connections and reduces code duplication. Code duplication means when we have multiple modules and those modules are connected to the same variables, that time we have to redeclare the signals again, right? So in each module we have to declare the signals. So that leads to the redundant code, that leads to code duplication. So it by using the interface, it will reduce the code duplication, and it improves readability and maintainability. Direction control using mod ports, clocking block support. So this mod ports and clocking block we are going to discuss in detail in upcoming videos. Okay, so this mod ports is used to give the direction for module signals. If you see in Verilog, in port list, we will give either input or output or in-out. This direction only we will give, right? But when we use the mod ports, we can give multiple direction for the same signal. You can give input also, we can give output also, based on the module's role, whether it is a master or slave. Okay, so that is the use of mod ports. And clocking block is used for synchronization. So synchronization in the sense at what time your signal has to drive, what time signal has to sample, this thing we can give. It will give the input and output skews for the signals. Okay, that is the use of one clocking block. And it is used for encapsulation of protocol logic. Encapsulation of protocol logic in the sense, you can insert the logic also inside the interface, okay, by using task and functions. And virtual interfaces in verification, parameterization and flexibility. That means we can use the parameters inside the interface, and that allows same interface definition to be used with different configurations. And better hierarchical structure. Better hierarchical structure means interfaces can be designed hierarchically. That allows better organization, and it will reduce the clutter when we are connecting multiple modules. Okay, so this is the need of interface. Now we will see example without interface. Here I have a module called memmod, and inside the port list I have multiple signals, and here some logic and module. One more module is there, that is CPU mod. Few of the signals are same here, and some logic and module. And this is the top module. Inside the top module, I'm redeclaring all the signals. Whatever the signals I have used in CPU mod and mem mode, I'm redeclaring here. And here I'm instantiating this CPU mod and mem mode. If you see here, I'm redeclaring the signals every time, right? Here also. So this leads to code duplication. This is without interface. But when we use the interface, this is the example for with interface. Here I have a interface. Interface is a block that starts with interface and ends with end interface. And here all the signals are included. Whatever the signals I have to connect between CPU mode and mem mode, that will be included in interface. Okay, and this is the mem mode module. Here, instead of declaring all the signals manually, what I'm doing, I'm just passing the interface. Simple bus is the interface name, and A is the handle for the simple bus interface. And here I'm explicitly taking the clock because I have not included the clock in interface. That's why I'm declaring here. Okay, and this is some logic in the mem mode, and this is the CPU mode. Similarly, I'm just passing the interface and taking clock. That's all. Here I'm not declaring all the signals, right? If I declare all the signals, it will take multiple lines again. So instead of that, I'm just passing the interface to the port list. And in top module, I'm declaring the clock and I'm instantiating the interface. Interface is nothing but simple bus here. and SB interface the handle for simple bus, and here I'm instantiating the modules. And if you see here in the port list, I'm passing the interface. This is by position and this is by name. Dot we are using, right? So dot means by name, and just if you are using comma, and this is by position. So here instead of declaring all the signals multiple times, we are just passing the interface handle. So when we are writing the signals also in Verilog, in the last example we have declared the signals, right? That time you have to take care of positions, otherwise port mismatch will be occur. So to avoid that, we can use simply interface. And one more thing is, in both modules, mem mode and CPU mode, you have used different names for the interface. Simple bus A you have used, simple bus B you have used, right? A and B you have given. So if you give the same name for the interface in both modules, then we can do the implicit port connection. And if you see here, I have given the name SB underscore interf for the simple bus interface, and for CPU mode also I have given the same name SB underscore interf. So in the top module, I can write dot star for implicit port connection. So that means it will implicitly declare the signals. Okay, in order to perform implicit port connection, you should have the same name for the ports. Okay, so this is about with interface. Now we will see the important points to remember in interface. An interface is a bundle of signals or nets that communicate between a test bench and DUT, design under test. The interface is instantiated in design and can be accessed through a port as a single item. We have already discussed, right? It can be instantiated in design, that is nothing but a module, and can be accessed through a port as a single item by passing the interface. An interface can have parameters, constants, variables, functions, tasks, functional coverage, and assertions. These are all the things we can include in the interface. And interface definitions can take advantage of parameters and parameter redefinition in the same manner as module definitions. That means how we use the parameters in modules, same thing goes for interface. Okay, and redefinitions also. That means how to override the parameters in module. Same thing happens with interface. In addition to task or function methods, an interface can also contain processes, initial or always blocks, and continuous assignments, which are useful for system level modeling and test bench applications. That means we can use the procedural blocks inside the interface, that is initial or always block, and we can use continuous assignments also. And also we can use task and functions. This is one important point. Okay, we can use all these things in interface. And interface specifies the directional information using mod ports and timing information using clocking blocks. Interfaces can be declared and instantiated in modules, but modules can neither be declared nor instantiated in interface. That means we can declare and instantiate the interface inside the module, but inside the interface we cannot instantiate or declare the modules. Okay, this is one thing. An interface can be instantiated hierarchically like a module with or without ports. That means inside the interface we can have another interface and we can instantiate it hierarchically like a module. Logic is recommended in the interface because inside the interface signals can act as both input and output. That means when you are declaring the signals inside the interface, we have to use the logic data type for the signal, because if you use the reg data type, that can be used in procedural block. That means it is used to drive the procedural assignments, and if you use the wire type, then it is used to drive the continuous assignments. But when we use the logic data type, we can drive both procedural assignments and continuous assignments. That's why we have to use the logic. Logic is recommended in the interface. Now we will see generic interface. What is generic interface? A module header can be created with an unspecified interface instantiation called a generic interface. Generic interface is nothing but an unspecified interface in the module header. If you remember in the last example, in CPU mode and mem mode, I have passed the interface with the name, right? I have given the interface name. I know that I'm using the simple bus interface, right? Simple bus A, simple bus B I have given. So that means I know that I'm using the simple bus interface. But when the interface you don't know the interface. So when the unspecified interface you have used in the module header, then it is called a generic interface. That means you just declared as interface A, interface B. Instead of giving the name of the interface, you are just using the keyword interface A, interface B. So that interface is called as a generic interface, and this interface can be specified later on when the module is instantiated. That means this unspecified interface can be specified later when the module is instantiated. And an implicit port cannot be used to reference a generic interface. So for the generic interface, when you are using interface A, interface B, that means generic interface, you can't do the implicit port connection. Okay, because that is unspecified interface. We don't know which interface we are using, right? That will be known when the module is instantiated. That's why we cannot do the implicit port connection. This is the example interface I have. This is mem mode. Here what I'm doing, I'm passing interface A. So I'm not passing simple bus A, I'm just using interface A and interface B. And in top module, I'm declaring the interface and I'm giving the name now. See, SB underscore interf, and this name I'm passing dot A and clock. So here I'm writing, I know that okay, SB interface I'm using. So before that, this CPU mode and mem mode doesn't know which interface it is using. So this mem mode and CPU mode can use any interface. So this interface is called as a generic interface. An implicit port cannot be used to reference a generic interface. A named port must be used to reference a generic interface. This is one point to remember in generic interface. You cannot do the implicit port connection. You have to use named reference. Okay, named port must be used to reference a generic interface. Here I'm using the name. Now we will see task and functions in interface. We can write the task and functions in the interface. So this is my interface, simple bus, and here I'm passing the clock, and here I have included all the signals that are required to connect. And here I have defined the task master read and here slave read. So how you write the task in the module? Similarly, we can write in the interface task master read and here some logic, and task slave read, here some logic. And one more point is extend task mem task 1. So this mem task 1 is a interface task, but we have defined it in the module. So when the task is defined using the hierarchical name, then it must be declared as a extend task in the interface. So if you see here, this is my mem mode module. Here I have defined this mem task 1. Okay, this mem task 1 is an interface task, but I have defined using the hierarchical name a dot mem task 1, right? A dot means interface name. So here interface A, this is, here I'm using generic interface. Okay, here unspecified interface means generic interface a dot mem task 1. So when the task is defined using the hierarchical name, then that task must be declared as extend in the interface. So this task is a extend, this is outside the interface, right? That's why extend keyword. So if you have used mod ports, then you have to use export keyword. So we will discuss in the mod ports video. So for now, you know that extend keyword we have to use when the task is defined in using the hierarchical name. We have to declare using extend keyword. And some logic is there inside the mem mode. Here I'm calling the a dot slave read. So whenever you want to call that method, you have to use the interface handle a dot slave read. And in CPU mode also some logic is there, and I'm using b dot master read because b is the interface name, b dot master read, and you can pass the variables also. Here I'm passing this r address. Okay, and this is top module. Here I'm just instantiating. So, subroutines can be defined within an interface or within modules connected to the interface, enabling more abstract modeling. Subroutines is nothing but tasks and functions that can be defined within the interface or within the modules. A function prototype specifies the argument types, directions, and return values of a function defined elsewhere. That means function prototype. In the last example, we have seen extend task and some task name. So that is a prototype of a task. So you can write the function prototype also that specifies the argument types, directions, and return value. And if you are using task, everything will be same, but it will not return any value. A task prototype specifies the argument types and directions of a task defined elsewhere. And mod ports can use subroutine prototypes or just the identifiers with import and export concepts. So mod ports is used to give the direction for the signals, whether it is input or output. But for function and task, how we will give the direction? By using this import and export keyword. Okay, so this we will understand in detail in upcoming videos. A full prototype is required when importing a subroutine from another module or when default argument values or argument binding by name are used. So this point is important when we are using the mod ports. Okay, while importing or exporting the task or functions, this prototype, when to use full prototype or just identifiers, this thing will be important when we are using the mod ports. There I will explain fully. Okay, the number and types of arguments in the prototype must match those in the subroutine declaration. That means in the prototype, if you have declared 2 arguments, then while defining the task inside the module, there also you have to declare only 2 arguments. The number and types of arguments should be same. Okay, that should match. If a default argument value is needed, it must be specified in the prototype, and if different values are provided in both the prototype and the declaration, the value in the prototype is used. So when you give the different values in prototype and in the declaration, that time prototype value will be having the higher priority. Okay, so if the default argument value is needed, it must be specified in the prototype, and if different values are provided in both the prototype and the declaration, the value in the prototype is used. Formal argument names are optional unless default values, argument binding by name, or additional unpacked dimensions are declared. So these formal arguments names are optional. Okay. Formal argument names in the prototype must match those in the subroutine declaration. This is here only. Here I explained. Formal argument names in the prototype must match those in the subroutine declaration. This is normal how we write the task and functions in modules. Similarly, these rules are common. Okay. An elaboration error occurs if a module connected to a mod port with an exported subroutine does not define the subroutine. So that means when you are using the mod ports inside the interface, inside the mod port only we use the import and export keyword, right? So this exported subroutine, that means you have declared the task inside the mod ports, but you have not defined in the module. Okay, define in the sense writing the task. So you have not written the task, but you have declared that task inside the mod port. That times it will lead to the elaboration error. So elaboration error occurs in the elaboration time. Elaboration time means what? After the compilation and before the simulation. We know that compilation time, simulation time, right? Compilation error, simulation error we will get. Similarly, elaboration error. This will come after the compilation. Okay, after the compilation and before the simulation, this elaboration time will come. There, this elaboration error occurs. An elaboration error also occurs if the subroutine prototype in the mod port does not match the subroutine defined in the module. So both are same only. Subroutines defined using a hierarchical name must be declared as extern in the interface or as export in a mod port. So this thing we have already seen in the last example. So when you're defining the task inside the module by using the hierarchical name, you have to use the keyword extern. And similarly, if you are using the mod port, you have to use the keyword export. Okay. Tasks can be defined in a module that is instantiated multiple times, such as two memories driven by the same CPU. That means the module that is instantiated multiple times can define the task, because function returns a value, right? Function returns a single value. So we cannot write the functions, but we can write the task inside the module that's instantiated multiple times. Multiple task definitions are allowed through an extern fork join declaration in the interface. That means in the previous point we have seen that when the module is instantiated multiple times, for example CPU mode M1 and M2, two instances I have for the CPU mode. That time if you have defined the task inside that module CPU mod, then you have to use extern fork join, because you have two instances. Fork join means parallelly it will execute in both M1 and M2. For that you have to use fork join keyword, extern fork join and that task name. Okay, this will be applied for only task, not for functions. Okay, because functions returns single value. Now we will see virtual interface. So what is this virtual interface? Till now we have discussed what is interface and how to use the interface between different blocks. Blocks in the sense your modules. Okay. So in the Verilog test bench we know that our test bench is also module and your DUT is also module. So we can directly instantiate the interface in the top module and we can connect between DUT and test bench. Okay. So test bench is a module is a static. Module is static in nature and interface is also static in nature. So we can use interface in modules. But when we come to system verilog, we have a OOPS concept, right? We will use the class based test bench in the system verilog. That means we have a driver, we have a monitor, scoreboard. So this class based component we have in a system verilog. In order to use the interface in the class based test bench, your class is a dynamic, right? But interface is static. So we can't use interface directly. For that we need a virtual keyword. So by using virtual keyword we can use the interface inside the class. Okay, interface is static and module is static, so we can directly use interface. But when we come to the class based test bench, there we have to use virtual keyword in order to access the interface. So here I have DUT, interface and class based test bench. Okay, interface and your DUT can be communicated directly because both are static, so that will be compatible. So interface can be directly communicated with the DUT. But in class based test bench, your driver or monitor cannot communicate with the interface directly. So we can't directly declare the interface inside the class. So in order to declare the interface inside the class, we have to use the keyword virtual. So a virtual interface is a variable that represents an interface instance. So this virtual interface is a variable that is a handle for the interface that refers to the static interface. Okay, a virtual interface is a variable that represents an interface instance. Just like an object is a pointer to a memory address containing the class members, a virtual interface points to the interface. So just like an object, so class object is a pointer to the class members, right? Memory address containing the class members. Similarly, a virtual interface points to the interface. This virtual interface is also like a pointer that points to the interface, static interface. Okay. A virtual interface must be initialized before it can be used. It has the value null before it is initialized. That means when you declare the virtual interface, first you have to initialize it. before you are using the virtual interface, first you have to initialize it with the interface. So how we have to initialize, we will see in the example, but we have to initialize it before we using it. So because it has the value null before it is initialized. Attempting to use an uninitialized virtual interface shall result in a fatal runtime error. So if you have not initialized the virtual interface, then you will get the fatal runtime error. That's why we have to initialize it before we using it. And virtual interfaces shall not be used as ports, interface items, or as a members of unions. That means virtual interface we cannot use as a ports. Inside the port list we cannot pass it as a ports, and inside the interface also we cannot use it as a items. We cannot use it as a items, and we cannot use it as a members of unions. Okay, this virtual interface is just a pointer to a interface. It just points to a static interface. In order to access in the class based test bench, in order to use in the classes, we have to use the virtual keyword. Without virtual, you cannot use the interface inside the class. So this is all about virtual interface, and we are going to discuss about mod ports in next video, and after that we will see the examples for the interface, virtual interface and mod ports. Okay, thank you.